All right, UML, Unified Modeling Language. So we briefly met UML when we were looking at the logical design lecture. A general purpose software engineering modeling language, providing a standard way to visualize the design of a system. As we say, as I mentioned before, I think it's a very wide-ranging modeling language that covers a lot more than the class diagrams, which we're going to look at here, which is represent the logical structure of objects and their object hierarchies. Basically, class diagrams are the equivalent of ER diagrams for relational models, but for object-based models. Okay, I'm only going to cover the very basics of these. One reason is I simply don't know much more than the basics of it. And the other thing is that that's all we really need to know. You can always go into some more detail in your own time. Okay, so this is a basic class, what a class looks like in a class diagram. It's very similar to an entity in an entity relationship diagram. We've got a class name at the top. This one's a bank account. Then we have in the first box under the name, we have attributes. In this case, we've only got two attributes. We've got one owner, string, another one balance, which is how much money presumably you've got in your account. It's got a unit, in this case dollars, and equals 0 is presumably the default value, no money. When you open a bank account, you have no money, that's the default. And we've got underneath that, we have two methods defined or identified. We've got one called deposit, which is an amount in dollars, and one called a withdrawal in the amount of dollars. So that is that's how to draw a class in a UML class diagram. We don't need to worry about the details of what deposit, how, and withdrawal, how those methods actually operate. This is just about specifying what you could call the front end, the user interface onto the classes. Remember, encapsulation, the user shouldn't need to know how these methods operate. Yep? They don't need to know exactly how these are stored in the system. All they need to know is that these are the things, these are the attributes, and these are the methods that you can apply to an object. There are a variety of different types of class relationships that can be defined, and there is like in ER diagram, there's a notation for defining the different types of relationships that exist. Unlike ER diagrams, which have no formally defined notation, UML has a defined notation. UML, by the way, is managed. It's one of these international consortium. They decide the standard that is UML. So again, it's one of these international consortia decide what is in UML and what isn't in UML. And here's some of the different types of relationships. Now, I'm only going to really deal with, we've seen inheritance, the ones we've already seen, inheritance, aggregation, and composition. I'm not going to deal with some of the others, although we might see them on diagrams and I might mention them. So let's have a little look. Okay, inheritance. Okay, inheritance, I've already mentioned it, it's just this triangle symbol, or arrow as the case may be. I think of it more as a triangle than an arrow. Here we've got a student, text, module, and personal information. In this case, the student is inheriting the information. We've sort of drawn it the other way around than what I did previously. So a student has an address, a phone number, a mobile number, an email, number of emails as a list, as well as a name and a list of modules that they're attending to. So a student is inheriting personal information. A staff member could also inherit personal information. Perhaps a contract worker might as well. So this personal information can be inherited by more than one different type of class. That's how inheritance is drawn, as simple as that. Two forms of composition, aggregation and composition, okay. So these two filled and empty diamonds are used to represent these two types of composition. So an aggregation composition is where the one object, the object that encloses the other, contains the other object, so that the contained objects can exist independently of the containing object. Okay, so students, so if the circle is class, as in what we're in now, you exist outside of the class, but at the moment you're aggregating here. This class that I'm teaching is made up of multiple students, but you exist outside of this class as well. Whereas composition relationship means that the property object cannot exist without the other object in place. So for example, you couldn't have a car object without an engine, or the engine object couldn't exist without being within a car object. Now, I'm not saying that that's a sensible model of the world, but it's just the model that's drawn here. So composition means that the object that's the property of another object cannot exist without the enclosing object. Aggregation, it can exist without the other object. So we get this kind of example. So now we've got a student is inheriting the personal information. Also, the students are aggregated into a class, a student list of classes, one list of classes, many students, and it's an aggregation relationship. So we're starting to build up this object diagram of the relationship between students and attributes. So as a nice exercise for you, you can remember your ER diagram of students in the university, try and turn it into a UML diagram. That's a nice little exercise for you. Maybe we should do that in the practical afterwards if we're so inclined. And that's really all I want to tell you about the UML diagrams, because, as I say, that's probably about as much as I know about them. Now, here is the OGC simple feature model. Remember, the simple feature model is defined by the OGC, the organisation, I can never remember what OGC, Geographic Consortium, whatever it is. And it is the standard defined for storing spatial data. And it is a model that underlies the spatial model in PostGIS and indeed in many other systems as well. Basically, if you're doing spatial vector data, you should have a reason not to be following the OGC model to a certain extent. And we can see it's made up of a variety of objects. We don't have the methods and the attributes listed on this diagram. Why? Simply because it would become probably rather too complex. There's always a balance between the ER diagrams and UML diagrams between showing lots of objects and showing the details on the objects. And it's always a balance between detail and completeness and sort of coverage. Okay, so what I'm going to do is make our way through a small section of this, the most simplest part of this section, which is the point, line, string, line, linear ring curve relationship, with an attempt to sort of understand how to read this diagram and start to understand the basics of the OGC model itself. I'm not going to go through all that diagram in detail. It would bore me, never mind yourselves. Right, so points. Okay, so this is directly cut and pasted out of the OGC, the PDF that distributed from, so if you search OGC simple features model and you get the definition document from the OGC, this is directly cut and pasted out of this. Okay, so this is what we get with this is the associated information that goes with that class diagram. So first of all, here's the point diagram. It provides us with a definition of the point. Remember, every object, every entity in an ER diagram, every object class that you ever define, or every entity in an ER diagram or needs a definition, and that definition should be as unambiguous as possible. So it says a point is a zero-dimensional geometric object. Yes, represents a single location in the coordinate space. Has an x and a y coordinate. It may also, if the spatial reference system that's going with that point is appropriate, it may also have a z and an m attribute as well. Z, unsurprisingly, is elevation. M, do you know, anybody know what M is? Is precision, basically, I think, if I remember correctly. Precision, yeah. So it's a measure of precision, yeah?
When you said that you define the entity or the attribute in the ER diagram, or you justify it, where do you do that in the ER diagram?
The attributes in an ER diagram, well, it would be in the...
No, where do you define them? You said that you define...
Ah, well, yeah, okay, so here's your definition. Now, okay, so this is interesting. So this is interesting. So they've got, here they've got the values, so they're doubles, 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 doubles. Okay, what these actually are is that they're calling them as a list of methods. Remember, encapsulation, you're only allowed to interact with an object through its methods. Okay, so a point object only has two, three, or four attributes, yeah, properties. Those are, we don't, if we're following encapsulation, we don't need to know what those properties actually are. All we need to know is the ways that we can interact, the methods that we can use to interact with those properties. So in this case, they've defined methods x, y, z, and m. So this is, I think, a list of methods, and it's things that you can do to the point object. And it just happens that in this case, the methods, what you can do, set and get the values for these things, match onto the list of attributes. There's nothing else that you can do, I think. Maybe that's answering what you said, your question. Maybe I've just drifted off and talked about something else. I'm not sure. Okay, so when I looked at this, I thought, is that a list of attributes or is that a list of methods? It certainly says methods here. So what I suspect is that there's a method that's, what they're saying is you can get and set the x coordinate, you can get and set the y coordinate, you can get and set the z coordinate, which are actions, things you can do on the object, but they happen to all map onto just changing the one value, one property value in the object itself, the instance of the object. But it's not clear. I think that's an interesting thing. It's not clear to me how they're differentiating between attributes and methods. And it may be that this is a logical model and that different programs allow you to, basically you can implement these in different ways in different programs. Okay, so it's a simple thing. It's got x, y, possibly a z, possibly an m. And if we go back up again, remember that coordinate system business. Here you can see we've got an association relationship between a geometry and a spatial reference system. And of course, if we follow our hierarchy, we can see that point inherits from geometry. So the point inherits the associated spatial reference system. Association is just a pointer, basically, to another object. So here, the geometry class is pointing to the spatial reference system, but the point inherits the geometry class, so it also inherits that pointer to the spatial reference system. If the spatial reference system supports z and m coordinates, then the point inherits those z and m coordinates from the geometry. Right. Okay, so points, relatively easy. A line string here is a curve, okay? It's a type of curve. Look, it's inheriting from curve. You can turn these triangles into type of relationships. It's a type of curve in which there is linear interpolation between points. Okay. Each consecutive pair of points defines a line segment. Okay. So a line string is made of two or more points in a string. Yeah, it's an aggregation. Points can exist outside of line strings, so it's an aggregate relationship. But a line string must have at least 2 points, too many points. So it's a set of points. How do you go between those points? It's linear. Now, we could fit some kind of spline between those points or some kind of curve between those points, but we're not. It's linear. It has to be linear on a line string. Okay? So a line string has methods, the number of points in the line, and we also have a way of getting each point out of our line. So it returns a point based on, we know how many points are, we can go, give me point 1, give me point 2, give me point 3. Okay. So that's a line string, is a set of points linear between them. A line ring, which as we can see is a type of line string. A line ring is a string that is both closed and simple. This is why it's called the OGC simple features model, is because it's about modeling simple features and it doesn't work for complex features. A simple feature is a feature in which case in a line in which the line does not cross itself. So it's a non-crossing line is a simple feature. So for example, figure 2, so we can have a string, we can have a simple line string, start and end. We have a non-simple line string which intersects itself. We have a simple closed line string where the start and end points are in the same location. And we have a non-simple closed line string here in which it crosses itself. So simplicity is about not crossing over, basically. Okay, so a linear ring is both closed, so it's a type of line string that is more specialized because it's closed and it's not crossing over. Okay. So item D is a closed line string that is not a linear ring because it's non-simple. Okay? Two linear rings. These aren't linear rings. These are linear rings because a linear ring, sorry, this is a linear ring because it's simple and closed. Right. Simple rings. A curve. The last one on this little section here. What's a curve? A curve is a one-dimensional geometry object, so a line, usually stored as a sequence of points. That usually worries me there. When is it not a sequence of points? With the subtype of curve, specifying the form of the interpolation between the points. This standard defines only one subclass of curved line string. So basically, curve at the moment, basically it doesn't really do anything as far as I can tell, but it's where you could start implementing alternative models to linear between points. So you could start implementing, say, splines fits between points or various curves, smooth curves between points on a line string rather than just linear between the points on a line string. Okay, so clearly that's just one little, this is just this one little portion of the diagram. Clearly we can see we've got a whole load of other features over there, and I think we're just going to quickly pop over and look at multi-line strings because I think that's helpful if I remember correctly. Yes, So just to finish off all the lines, basically, we can see that a multi-line string is a aggregation of line strings. So multi-line strings, it's what you would think of in ArcGIS as multi-part geometries. Yeah? Familiar with multi-part geometries in ArcGIS? Very, very slight nodding. Doesn't convince me that people are very particularly pleased with it, particularly knowledgeable about it. But a multi-line string is a multi-curve whose elements are line strings. So basically, it's made up of more than one segment in your line, or more than one part. So here's an example of some multi-line strings. This is one line, a multi-line string up made of two line strings, one S1, E1, the other one S2 to E2. This is a non-sim, so we've got a simple multi-line string, a non-simple multi-line string with two elements. So here, our first line is non-simple, it crosses over. It's made up of 1, 2 line strings. And our final one over here is a non-simple closed multi-line string with more than one element. So here we're starting here, we're going round something like that by the look of it, and then we've got the second part like this. Okay, multi-line strings, basically multiple line strings. All right, quite a short lecture this week. Okay, just to summarize objects, the object model. As I say, it provides a very powerful, intuitive data model. And the power and the intuition comes through the idea, the concepts of the classes, what you're defining in the world, and how they're defined. The inheritance relationships between classes, which allows you to share behavior and properties across multiple objects. The idea of composition, that you can embed objects within other objects and establish these composition relationships. And then the ideas of polymorphism, that there should be one way of dealing, that sort of the idea that you deal with what you're, that you specify the things that you can do in a simple semantic way. Okay, so if we don't, if we want to move something, we talk about moving it, not necessarily driving a car, walking, cycling a bike, whatever. It's all about moving, and we work at the level of moving because it's all about moving rather than the individual ways in which different things move. Okay, so you just have to work at the level of moving rather than how particular classes and objects move. And the final concept is this idea of encapsulation, that everything's there in one space, that you don't need to, that you just, once you've got your objects, you can only interact with them through the defined interfaces, the defined methods on those objects. You cannot hack an object. Now, the reality is in many programming languages, you can hack objects, but in the sort of ideal world of the object model, you would prevent people doing that. That shouldn't be part of it. And things like Java and C++ languages, heavily purely object-oriented languages, implement all of these, or the vast majority of these concepts, these object concepts. Things like languages like Python and JavaScript, which, well, we're not going to meet Python, but we'll meet JavaScript next year. We'll also meet PHP. These implement a subset of these properties to a certain degree. So they're sort of, your object purist would say that's not a pure object-oriented language, but they do support an awful lot of the object concepts and the object way of doing things, while not ticking all the boxes for being purely object-oriented. Okay, so what's the object? What's the market of objects, so to speak? The object market in the world. Well, in the original first lecture, introductory lecture, I think I talked about, or was it the second one? I can't remember. talks about object databases. It's a relatively niche market still for object databases. I think the figures I've seen are between 10, 15% of databases and object-based databases out there. Very difficult to get actual figures. Tends to be in complex domains. So, for example, I believe they're very popular in airline booking systems. They're popular in network models, transport models, things where you've got complex behaviors, large systems. The object model can be quite important in a database situation. It is a really, really important way of programming and approach to programming, and we'll see that in more detail next year. You organize your code into objects. It's a very powerful way of supporting programming. We've seen logical modeling as UML class diagrams, the basics of it. And we've seen that the OGC simple features model is an object model. It's designed as an object model, but of course, as we know, it's implemented in Postgres through a combination of relational technologies and object technologies that work on. That's basically, you're storing your objects in a relational database structure. That's what you're doing in an object relation.